Hi everyone, thanks for watching. In this video, I'm going to show you how to write transmutation equations, which is a way to describe how unstable nuclei decay. Before we do that, just remember from the last video that there's lots of different types of radiation that can be emitted by unstable atoms, three of which, the ones we deal with most times, are the ionizing radiation of gamma rays, alpha particles, and beta particles. Before we actually look at any transmutation equations, let's also remind ourselves of some of the correct isotopic notation symbols for each of these three radiation types. For gamma rays, we use the gamma symbol 00 because it's just a wave that has no mass. Alpha particles are made of 2 protons, so an atomic number of 2 with 2 neutrons attached, totaling to a mass of 4. And there's no electrons, so the charge is technically +2. And beta particles, we use a lowercase e because they're just electrons, -1 for the atomic number, and 0 mass because electrons have 0 mass. We're actually going to keep those symbols in this key idea box up here, along with the symbols for a neutron and a proton, because you'll have to use those from time to time as well. Finally, we can look at an actual transmutation equation example. Like we've already said, it's simply just a way to model and describe how an unstable nucleus decays. It can also be used to show some other nuclear changes, but we're going to stick with decays at first as kind of like the easiest example. So this first decay example we're going to look at is that of an alpha decay. In this little diagram, which is simply a nucleus that is unstable, and like all unstable nuclei, it's going to decay. But as an alpha decay, it does pretty much what you'd expect it to do, and it's going to be emitting an alpha particle. That's any nucleus that undergoes an alpha decay emits an alpha particle. So I'm going to show you what that looks like with this nucleus. At the same time, we're going to write out this transmutation equation, which is simply a way to sort of write on the page or on a piece of paper or anywhere. It's a way to write down and describe what's happening in this nucleus. And it does it in a before and after fashion. That's how I want you to think about these. And we know what the nucleus looks like before the decay happens. There's a picture of it right here. So to start off, you just write the isotopic notation for whatever the nucleus is before the decay happens. So you count the protons. I see there's 6 of them. So you put the atomic number as 6. I happen to know that 6 protons is carbon. If you didn't, you would go to a periodic table and look it up. If you count the neutrons, there's 8 of those, making the total mass 14. Now that our before symbol is written down, we can go ahead and with the nucleus get a visual of what the decay looks like. Remember, a decay just means that the alpha particle gets emitted or given off. So an alpha particle, 2 protons and 2 neutrons, goes flying off. It is now separated from the original nucleus. To represent that in the equation, you put an arrow. The arrow represents that a change has taken place, and then after the arrow you put the isotopic notation symbols for whatever particles you're left with after, one of them being my alpha particle right here. So you can use our little reference up at the top of the screen. Alpha particles are 2 protons with 2 neutrons, totaling to a mass of 4. That's not the only particle we have after the decay, because there's also what's left over of the nucleus, which has, count them, 4 protons, so an atomic number 4, and it looks like there's 6 neutrons, so 4 plus 6 gives me a mass of 10. Go to the periodic table, look up whatever atom has 4 protons, and you'll see that it's beryllium, symbol Be. So you fill in that symbol for the 2 particles left over after the decay takes place. So now that it's done, let me just neaten that up a little bit there because my writing's kind of sloppy. We'll make one more final kind of observation, a really important key idea, and that is that the atomic numbers and masses on opposite sides of the arrow will always equal one another. This is going to be extremely important when you start writing these equations yourself. If you haven't noticed it yet, take a look at the numbers in red. We started with a mass of 14 before the decay, and after we have a total mass of 14. That's always going to be true. It works with the atomic numbers as well. We started with 6 protons, and afterwards, 2 plus 4, we still had 6. Like I said, this is going to be extremely important and helpful when you start writing these yourself in the next video, which actually concludes this video. Thank you very much for watching.